We're in chapter 34. The last section was on plane mirrors, that is, mirrors that are totally reflective and flat, section 34.1. We now begin section 34.2 on spherical mirrors. Now, spherical mirrors can be viewed in two ways. We primarily use spherical mirrors because they're inexpensive to manufacture, and they are part of a sphere. If I can imagine a sphere here, and therefore these mirrors have a radius r that would be the radius of the sphere that was constructed. Now, if we view the mirror on this side, we see that the mirror is, this would be the center here. We see that this mirror would be concave, but if we viewed it on the other side, it would be convex, or shaping outward. And in either case, we find that the focal length is defined as the distance of the image from the mirror of an object that is at infinity. And this will be true not just for mirrors, but also for lenses. So the focal length is defined as the distance of an image from the mirror when the object itself is at infinity. And one can prove that for spherical mirrors that this focal length is always the radius divided by 2. Now, for mirrors that are spherical, and for lenses that are spherical, these formulas are approximate, and there's some aberration. The perfect formula, or mirror, would be one that would be parabolic. And that is because a parabola has the properties of being that surface such that the light from a single point going anywhere to the mirror will go to infinity in this direction like this. This almost happens for a spherical mirror if we're near this center part, but as we get further and further out toward the edges, we get anomalies where that reflection is not perfect. So another aspect of the parabolic, this is parabolic. This is spherical. And for the spherical mirrors, we approximately achieve this, but not exactly. So light that goes out from this point will go this way. Light that goes to this point will go this way. But if you really look carefully, you'll find that these are not exactly true, and there's some dispersion out here for both of these mirrors. Now, this equation here is very important because it tells us whether the mirror is spherical, whether it's convex or concave. This still applies and gives us the focal length. And this can be shown using ray diagrams. A parabolic mirror is very expensive to make, and therefore we almost never see those, or in lenses. So they're not honed exactly in that shape, this parabolic shape, because of the expense. And we're going to do ray tracing to look at objects that issue both from convex and concave mirrors. Again, we're going to take our objects to be like arrows, and if we put it on this side of a mirror, and this is the object, then we find that this mirror right here is considered to be convex. If we take our object and put it in front of a mirror that's shaped like this, we consider this to be concave. We'll get into exactly how these mirrors give these different images, but generally speaking, a concave mirror is going to give an enlarged upright and virtual image in front of the mirror. There's an exception, and we'll discuss that. A convex mirror is going to give a diminished upright and virtual image behind the mirror. You can remember that second one very easily because you've seen spheres that are in a garden, and when you look at these reflective spheres, you can see the entire garden behind you. You walk up to one of these, it's usually sitting on a platform, a reflecting ball of some type, and as you look in there, you see all of the trees and the buildings and everything in an upright position, but small, as though they're contained within the sphere. So that's one situation you're familiar with. In the next section, we're going to get to the exact formulas for both the convex and the concave mirrors and see what that gives us.